This project is about the development of long-range, low-powered, and smart IoT device for detecting illegal logging in forests. Beyond doubt, we can all agree that climate change is real, and illegal logging is one of the factors contributing to global warming. We must have heard of wildfire, drought, etc. in some part of the world, in the US, for instance, and this is because of climate change. And illegal logging in some part of the world has been seen to be contributing heavily to global warming. So there are different ways to curb illegal logging. We have the traditional means where forest guards are being used. But this approach is so sustainable because a lot of resources goes into this in empowering these guys that monitor the forest. Another approach we can use is the automatic approach, which in the age of technological improvement can be seen to be more sustainable. So in this project now, this is the framework that we are working with. So we are assuming that if we have a forest, we can have several nodes. What each of these nodes does is that they get the sound around each location within a circumference, then get the location of the node itself, and based on the TinyML model that will be uploaded on this node, the sounds can be the sound class, can be inferred in order to know whether logging or no logging activity is happening at that point in time. And then we can send the decision through LoRa module to the gateway. And through GSM data transfer, the gateway can send the sound class and the node location to the cloud. In the event of logging, an alert system can be integrated in the cloud environment in order to alert those forest inspectors or officers in order for them to take action, basically. This is the flowchart of the node to node communication that we used in this project. Sensor will be available to get sound and GPS information, and the sound will be read and digitalized. This is the sender node now. At this point now, the sound will be preprocessed and classified using the TinyML, and the GPS information will also be captured. And because we are going to be using LoRa communication, LoRa packets will be sent so that the GPS information like the latitude, the longitude, and the sound class, whether logging or no logging activities have been detected. So this will be broadcast. When the LoRa packets are sent at the receiver node will be waiting every time to get the packet. So based on the packet type, if it's one, there will be an information that the GPS packet has been received, and the GPS location will be read, the longitude and latitude in this case. And if it's packet type 2, the sound class package will be read at the same time, and further information will be sent to the cloud server. So that's how the point-to-point communication from the sender node and to the receiver node works. In this video here, we have two nodes, that is the sender node and the receiver node. So the sender node is sending the GPS and the sound data to the receiver node, and the receiver node is receiving it and storing it temporarily in this SD card. So this was used in order to test how point-to-point communication works in the lab. For the prototype, I developed this prototype, and this prototype actually has two microphones collecting sound in order to have a form of redundancy in the system. And the idea behind this is that if one of the microphone is not working, then the other one should give an information that is sufficient enough for the nodes to function as it is required. So this is the LoRa module for the communication, and this is the GPS. We use the Raspberry Pi Pico as a microcontroller. You can see some wires, and this is the charging module. On this case here, we have the solar panel in order to make sure this system work 247. This is me here when we went to Kenya for the field trip. You can see me holding two nodes there, and we try to test point-to-point communication. You can see that we were able to achieve close to 1 meter in this particular forest that was used in Kenya. It's called Ngong Hill. So in this particular location in Kenya, we're able to achieve about 1 meter point communication of the node. Of course, more work to be done about this device, but we've been able to prove that we can design a node with some cheap components, and this node can get data, and through the power of AI, we can get the class of this data, whether login or no login is happening. And this data can be sent through LoRa, because in forest area, why we need to use LoRa, because in the forest, there is no Wi-Fi, and the network is really poor there. So we rely on a form of communication uh, that is called long range, right? LoRa. Depending on the side of the antenna, this LoRa could go as far as 10, 20 kilometers. But here we are able to achieve about 1 kilometer in our test. So uh, we're still working and still trying to look for avenues to improve the device. And this project was done by ourselves my team at the University of Huddersfield, guys at Strathmore University, and we also have a team at University of Neuchâtel. And our own part of the project was to work on the node development. And the project was funded by Climate AI.